welcome to my session, Forensic Container Checkpointing Analysis. The first part of the talk will be about checkpointing, a bit background, and then how to use the checkpoint for the analysis of your container. My name is Adrian Reber. I work at Red Hat since about 2015. I'm involved in process migration, so when talking about checkpointing, the basis is kind of process migration. I'm involved in that for over 13 years now. And everything we're doing with checkpointing in Kubernetes today is based on CREU, a tool, and I'm involved there probably around 2012. And for the last couple of years, I'm mainly focusing on container checkpointing, container migration, and with this, let's go to today's agenda. Today's agenda looks something like, I will talk a bit about the background of container checkpointing overall. Then I will present a couple of use cases, why I think that container checkpointing, container migration might be a useful idea. Then I will talk about the actual forensic container analysis based on the checkpoints. This is the demo part. And then I will talk about the plans for the future with checkpointing in Kubernetes. CREU is the tool we use to create the checkpoints. CREU stands for Checkpoint Restore in User Space. There's a reason why it's named Checkpoint Restore in User Space. So Checkpoint Restore is a technology which exists for a long time in an operating system and has been used especially in high-performance computing, maybe over 20 years ago in Linux. And there were different implementations. Some were based on external kernel modules, which were never upstreamed. And then there was library preloading to intercept system calls, to record what your process has done. And the problem with all those approaches was that you had to prepare the process you want to checkpoint. It was not completely transparent to create a checkpoint. You had to load the libraries, and then you can make the checkpoint. So people started to implement something to support transparent checkpointing, and the idea was to make it all in the kernel. Around 2008, there was a patch set for the Linux kernel with over 100 patches to support checkpointing in the kernel, but it was never accepted by the community because it was just a really huge patch set touching almost every subsystem. So the in-kernel approach didn't work, and the next approach was CREU, Checkpoint Restore in User Space, because it's no longer in the kernel. CREU uses existing kernel interfaces as much as possible to get information about a running process, and later uses this information to restore the process. The information is mainly found in procpit and other things, but it's completely in user space today, and there's no additional functionality in the kernel besides delivering information about the status of the process, but that can always be used by other tools also. So the interfaces are not checkpoint restore only. From CREU, there are multiple integrations into existing container runtimes, engines, orchestrations. And the first one to mention here is OpenVZ. I never used it actually myself, but the people behind OpenVZ, they wanted something to have live migration for their containers, and so they invented CREU to live migrate containers in OpenVZ. And the important thing here is that CREU was developed for containers. In contrast to the other checkpoint restore implementation I mentioned before, they have been developed for high-performance computing, and CREU was for containers. And that's also the reason why we can today use CREU to migrate to checkpoint and restore containers as we do. So another interesting implementation or integration of CREU into a container engine is Borg. Borg is, as far as I know, Google's container engine. This is also, I've never seen myself. It's just when working at CREU upstream, we were in contact with people from Google, and they told us what they do with it. So basically what they do today is, from what we've been told, they use CREU to migrate low priority containers from one node to another node if resources are getting low. So if you have some high priority task running, and you see that the resources are not enough, then you can move the low priority container from one system to another system. We were told that before that they just killed the container and restarted it somewhere else, and then they lost the work the container has done. And so with CREU, the work is not lost anymore. Examples given were things like YouTube re-encoding, which can run in the background, which is not time critical. But if you have to start from the beginning, it's just some lost work. So it's the possibility to be able to migrate a container is helpful here. Then CREU is integrated in LXD, the container engine runtime. It's integrated in Docker, and it's integrated in Podman. That's something I've been working on in the last 5 years. And the reason I started to work on the Podman thing is to support checkpoint restore and migration there is I wanted to get it into CRIO. So I started with the work to get checkpoint restore in CRIO in 2020. This is now merged, and it was all done under the label or under the Kubernetes enhancement proposal forensic container checkpointing. So the first 2 links are the actual Kubernetes enhancement proposals. Then the third link is the actual pull request, and the last 2 links are links to blog posts how to use checkpointing in Kubernetes today. Especially the last link will give all the steps I'm doing in my demos later in detail. So if you want to try it out, it's all written down in the last link of this slide. So let's go to some use cases why it might be interesting to use checkpoint restore with your container. So the important thing to remember is if you have stateless containers, then you don't have to do a checkpoint restore because there's nothing to checkpoint restore. You can just restart it somewhere else and nothing is lost. So you have to have a stateful container if you want to migrate. If you want to migrate a stateful container, then you probably need checkpoint restore this way around. So one simple use case is something like reboot and save state. So you have your system running. It has a kernel, a blue kernel, and you have a container running there. The container maybe takes a long time to initialize, start, and you want to avoid the downtime, but you have to upgrade the kernel of your host system, the blue kernel. So what you do, you can upgrade the kernel, you can create a checkpoint of your container, write it to disk, then reboot the system, so it's gone, and then it reboots with the green kernel, and then you can restore the container much faster than going through all the initialization it usually does. And this way you were able to decrease the downtime even if you rebooted your host. So the other one use case is quick startup. It's a bit similar. And this is something people talk to me about, which they actually use in production. So you have a software as a service, something, a container which you want to provide to your customers. It takes like 8 minutes to start up, or 8 or 10, but you want to provide it really quickly. So what you can do is you run your container one time, wait until all the initialization is done, you create a checkpoint, write it to disk, and then you can quickly create copies of the container without going through all the initialization. And one of the companies I talked to who are using this, they say they are decreasing the time for the container startup from 8 minutes to like 15 seconds. So it's, in their case, it helps them a lot. So then the combination of those things is container live migration. You have a source system, you have a destination system, you want to move your container to the destination system. So what you can do is you create a checkpoint, write it to some storage, and then restore it one or multiple times or on the destination system. Another thing which I haven't thought about myself are spot instances, but people talk to me about that. So spot instances are like really cheap, but they can go away really, I think like 2 minutes is on AWS. You have time to evacuate a node if it goes down. So you can create a checkpoint of your work, of your pod, of your container, write it to storage, and then restart it on another spot instance without losing any of your previous work, and you can just continue running your container. This is also people use CREU in production for, so it's a use case people are already using in production today. Another interesting thing which I saw last week was Microsoft was talking about ChatGPT and how they implemented it, and they actually mentioned CRIU there, which was strange to me because it seems like a very specific detail, but there was a video, I don't know, 15, 20 minutes, and they talked about how they use CRIU. Interestingly enough, they never reached out to upstream CRIU, what they do with CRIU and ChatGPT, so we at upstream don't know that it exists. The only trace we have is this, the video we have seen so far. So next is then the forensic container analysis. So what I will do now is I will start a container in Kubernetes. It's a simple application. It's based on Fedora 38. It's a Python server, so I talk to it. It gives me a number. It increases the number. Next time I get the increased number. So it's stateful, but it's really simple. And I want to checkpoint the container, and then I want to analyze the checkpoint to see what was going on in the application. And the container will not know that it was checkpointed. It will continue running. And the idea behind the forensic container checkpointing use case is you have some suspicious container. You don't want to stop it immediately, but you can take a checkpoint. The container will not know that it was checkpointed, and then you can either restart it in a sandbox environment or analyze it like I want to do now. So, is the font big enough here? Can you see this? Should I increase it a bit more? Okay, so I have a simple pod definition here with two containers. It's basically just, so it's two containers which do the same thing. It's a web server which returns a number and then increases it. The one is Wildfly-based, Java-based. The second one I'm using now is Python-based. So it's a really simple setup here, and let's start the containers. And let's hope it, yeah, so both containers are working now. And now I can talk to my container here on port 8088. And you see it just returns counter 0, 1, 3. So it's a stateful container, but it's really simple. In addition to being able to stateful, I can force the container to create two files, so just that we later can have a look at those files. So I create a file called test file 1 and test file 2. And it also can store secret information in the memory. So this will just write the string random 1432 key to a local variable inside of the Python process, and I want to later find this private data in the checkpoint, just to show that I'm able to see things that have been written to the container. So this means a checkpointed container, I can extract private keys, I can extract random numbers and things like this. So whatever you think is secure in the memory of the container with checkpointing, you can write it to disk and later analyze it and see it. So the next thing I will do is I will create a checkpoint. So checkpointing currently is a kubelet only API, so I have to talk to the kubelet, which is this part here, 10,250. Then I'm using the checkpoint API endpoint of the kubelet. And then I'm telling it I want to checkpoint in the namespace default, in the pod counter, in the pod counters, the container counter. And then I'm writing the value of the checkpoint location to a variable. And I'm just going to show where it's written to. So it's just under there, var lib kubelet checkpoint, and then a tar file which contains the checkpoint. So just to my slides. So the next things I want to do is I want to use checkpoint control. We wrote a little program which gives you some information, initial information about your container checkpoint archives, and this is checkpoint control. So let's use checkpoint control on the tar archive. Where is it? Checkpoint control. Show archive, and now it tells us. I'm just gonna make the fonts. It's a table. It's a bit hard to read. This is what it's supposed to look like, and now let's zoom in. So we see now where's my pointer here? So we have a container named counter. This is correct. This is the image it was based on. The checkpoint is from a container named counter. This is the image the checkpoint container is based on, then the ID, then the runtime, when it was created, the engine, the IP address, the checkpoint size. So this is actually the size of all processes written to disk, all memory pages, all registers, all everything. And the root fsdiff size, this value is, so what we do in our checkpoint archive, we track all the files which have changed in comparison to the original image, and then we put those files also into checkpoint archive, and so we can see all the files that have changed in the container. Checkpoint control has a few additional things which are not readable here. I can see all the mounts basically my container has. So I see all the bind mounts, all the internal mounts, and things like this. And the last CREO dump statistics is the information CREO wrote, how long it took to create a checkpoint. And one example, you can see CREO scanned 7,000 memory pages and wrote around 2,000 memory pages to disk. Okay, so this is checkpoint control, which gives us some additional information, and then let's have a look at the checkpoint archive itself, and then we will use a tool called CRIT, which stands for CREO Image Tool, to look at the actual information about the processes now written to disk. So the first thing I will do is I will go to a directory. I hope it's empty, and now I will untar the checkpoint archive here, and which gives me those files. So the first file, bind mounts, is just an overview where we see the bind mounts for the container and how we need those information to later restore the container correctly. Then there is a file config dump, which is just the metadata about the container. A lot of things you see here was read by checkpoint control and written in the table. Then we have dump log. This is basically the log file which CREO created during checkpointing, so it might not be interesting. It's more interesting if something fails or things like this. And then the rootfs diff tar is interesting. Let's have a look at this one. This is all the files that have changed in the container compared to the original image. We can unpack that, and then we can have a look at those files. And this, from the name, it's the log file. So this is just the log file the Python process creates, the server process creates. And those are the files that have been created in the containers compared to the original base image. And we see it's just a test file. So we can see all the changed files compared to the original container. So if something was created in our container which doesn't belong there, we can easily see this here. So, but seeing files is not so, it can also be done on a running container, so this is not something totally new, but let's have a look at the checkpoint directory. The checkpoint directory contains the CREO image files. CREO image files are mostly in protobuf format internally. There are a couple of other things here which I can just quickly show is, for example, those files here. So what happens, so I talked a bit about mount points. So if during restore of a container, CREO tries to restore all the mount points as they were before. So if we have a bind mount, we just bind mount it again, that's easy. If it's some proc file system, then we just mount the proc file system again. But this is now actually, so there was a tempfs inside of the container, and what CREO does, it just does a tarball of the tempfs, and later we can untar the tempfs again and mount it at the right location in the container again. So this was just /dev, I guess, and the other one is with content is, no, it doesn't work. It's this one, I think. And this is just /sys fs c group, the content of there. But now let's have a look at the information about the processes in the container. So I talked about CRIT, so I can use CRIT show PS tree. This will show us a tree of all the processes in the container. And we see we have PID1, of course, in a PID namespace. We always need a PID1. It has parent PID 0, and then we have a PID 7 and a PID 8. And we see the information about the threads of the processes. We can just to get a list of the processes running in the container, I can do things like this. So I see I have processes 1, 7, 8 running in my container from within the PID namespace. And now I have the files core, and you see the core files, they have also 1, 7, 8, so they correspond to the PIDs of the processes in the container. And now I can do, for example, crit show core 1 image. And this gives me all the details about the process. So now I see the register, all the process had when we checkpointed the floating point, and so on and so on. At the end, I see the SE Linux labels. I see the restartable sequence information. So this is all the information about the process available for restore, which helps me then also to understand what was going on in my container at the at the time of checkpointing. For example, one interesting thing would be so I have the processes 1, 7, 8, and what are those processes doing? I see, so 1 is running bash, 7 was counter.py, and 8 was just the T command for the log file. And if I now compare this with a view from my host, I see the same thing here. So this is the process in my container, and I see again bash, I see counter.py, and I see the T command. The interesting thing here is if I view this on the system Kubernetes is running, I see the PIDs from outside of the PID namespace. CREU always has the information from within the PID namespace. That's why I was seeing 178. Some other things, for example, which is saved here during checkpointing is the information about namespaces. For example, the UTS namespace just has the information about a host name of the container. And then there's a lot of information you can find out here about process and all the details it was, all the mount points and all the things is here. So let's look at the content of the memory. So I've written my random key to the memory before, and now I can just use the grep command to look for it. And I see it multiple times in the memory. So so this way, just by using grep, I can find if I know what to look for information in the pages files, which are just a raw dump of the memory pages, which is now on disk. And another thing I can do is use GDB to analyze the processes in my container. So there's a script which converts a checkpoint to a core dump. So I created this, and now I have 3 core dumps. If I sort it by date, core 1, core 7, core 8. For each process, I get a core dump, and now I can use GDB to analyze to look at the core dump. And no, I don't want to enable debug info-d. And what's interesting now is that, for example, now I finally see the full command line here, because before I just saw bash, and now with this script, I actually see the full command line as it was seen also in my PS output before. And I can also look at the registers here, info registers. So again, I can see the same content I've seen before with my migrated tool. And yeah, so this is what I'm able to show here currently with forensic container analysis using the checkpointing, and then just a quick thing what we think what to do maybe next with checkpoint restore in Kubernetes. So currently we can checkpoint containers, we can migrate them with some additional steps. But we're basically only at the start at what we want to do with checkpoint restore in Kubernetes. The next step would maybe be to have something like kubectl checkpoint so that you can easily use without directly talking to the kubelet API. And then another thing we've been thinking about is doing pod checkpoint restore, not just single containers. So I've written already a proof of concept for this 2 years ago. So it's not a technical challenge. The challenge is more how to integrate it correctly in Kubernetes. Because for checkpointing a complete pod, we basically just checkpoint all the containers, collect some metadata for the pod, and then during restore we can then recreate the pod as it was during checkpointing. This is, from my point of view, it should be done. It's easy. Then maybe at some point we can even do some things like Cubectl migrate. We can just tell Kubernetes to migrate the container from one host to another. And if this works, maybe then we can have scheduler integrations, just like I told about Borg before. If there's a low priority container running and resources are getting low, then I'm just moving my container, my pod, to some other location. And you've seen my tar archive to work with the checkpoints. So we start a discussion at, to have a checkpoint image standard which we can push to a registry. So currently we have something for ourselves which we can push to a registry, a checkpoint, and which you can use to restore somewhere else. But we prefer to have a standard because there's a container format for checkpoints in containerd, and now I have done one in Cryo. I was not able to use the one from containerd because it's based on internal protobuf structures from containerd. So it would be nice just to have something standardized which we can all use, and which would make it just easier for containers to be migrated from one container runtime to another container runtime. So again, from my point of view, there's no technical reason that this shouldn't work, because in the end it all comes down to the checkpoint Creo created and some metadata around it. So once we have the image standardized, hopefully, but this discussion is going really, really slow. And with this, I'm at the end. So the summary from my session here is Creo can checkpoint and restore containers. It's integrated in different container engines, runtimes, orchestrations. It's used in production by multiple people already for a long time. Some of the use cases I've shown was reboot into a new kernel without losing container state, start multiple copies, migrate running containers, better use spot instances, forensic container checkpointing like it's defined in the Kubernetes enhancement proposal. And with this, I'm at the end. Thank you for your time and happy to hear any questions.
Any questions? Anybody?
This might be very basic because I'm not really familiar with checkpoints, but regarding the size of the checkpoint and the time it takes to create it, from what I gathered from the presentation, it depends on on how divergent the rootfs is, how much we have in the memory at that time, and one that I am not sure is if the size of the initial container also affects it.
Yes, so the size of the initial container doesn't affect it. So if the initial container is pulled, then it's just we just do it on top of it. And you're right. I've done measurements about migrating processes and okay, this is wrong. But the biggest size is definitely the memory pages, because the more memory it uses, the more we have to scan the memory pages and write them to disk. And if your container has many changed files, then this can become huge, of course. So this can totally blow up. So the best thing would probably do is have a read-only container with a read-only FS. If you're looking for, if your goal is container migration with minimal downtime, then minimal changes to the file system are definitely helpful here.
Hello, thank you. You mentioned in the beginning where a checkpoint is used, and I was wondering if it's also used for the use case, like the serverless, the Kubernetes serverless use case, right? For example, Knative. They've also trying to implement a few methods how to improve the startup time of the container, and there's also some sort of, I'm not sure if it's checkpointing, or are you aware if it's also using checkpointing there? Because they have like 3 or 4 different measures how they can improve the startup time of a container, or there's kind of cold start, warm start as well, and I was wondering if they're also using checkpointing for that. So
I'm aware of serverless. People are interested in checkpointing, but I don't know if anybody really implemented something around Creo. Upstream Creo, we are not aware of any implementation around serverless. What we are aware is there is I think there are 2 projects trying to integrate Creo into JVM. So the JVM starts up, it does all the initialization, and then the JVM internally does the checkpoint. So the advantage, if JVM does it internally, then the JVM can drop memory pages it doesn't need, because it knows what it doesn't need for continuing things, or drop secrets and things like this. So there's work going on there, definitely. But besides that, I'm not aware of anything.
Maybe one last question? Yeah.
Just an addition.
I'm actually working on Knative, so no, we're not using it yet, but I will talk to him tomorrow to to make that happen.
Okay, one last question.
Thank you. I would like to know if there is some specific scenarios in which it's difficult or challenging to use the checkpointing. Like you mentioned before, like having the mount binds, you have to ensure that, of course, the mounts exist on the destination. Yep. So, like specific scenarios that are difficult or challenging.
Okay, yeah. So everything which uses external hardware is, at this point, probably not working. External hardware is something which is not going through the kernel. So this is a GPU, InfiniBand, things like this, because Creo cannot figure out the state of the GPU. So if you have something which is accelerated by a GPU, and it's mapped into your container, we cannot checkpoint it. There has been, or current Creo upstream has support for AMD GPUs. So AMD came along and provided code to write a plugin. So if you have something which is accelerated by AMD GPU, you can checkpoint the process on the host and on the GPU. That works. But the plugin system needs to be, the plugins need to be written for each specific hardware. And so AMD was at this point the only one doing that. Coming back to my mention about ChatGPT, Microsoft said they are using AMD and NVIDIA GPUs to use checkpointing. So I don't know what it means. So maybe they have written something we are not aware of. Okay, thanks.